All right, so this is for AP Physics C and Aerospace Engineering Honors, a debrief on orbital mechanics skills, circular orbit, homework number 2. As with the previous video, all units have to be in units of meters and seconds and kilograms and meters per second before you can plug them into any of these equations. And it's the same set of equations in the previous homework assignment. Well, planet E has a mass of 6.39 times 10 to the 23rd power kilograms and a radius of 4,900 kilometers. Calculate the orbital period for a satellite orbiting the planet at an altitude of 940 kilometers above the surface of the planet. Okay, so as we've done a couple of times, there's the radius of the planet, and then there's the altitude above the surface of the planet. And the orbit radius is measured from the center of the central body, in this case the planet, to the location in space going around the planet. So that's going to be the radius of the planetary body added to the altitude above the surface of that planetary body. So in this problem, if the radius is 4,900 kilometers and the altitude is 940 kilometers, then you add them together, and 9 plus 9 is 18. So you get 5,840 kilometers. Of course, in the formula, you have to enter that as 5,840,000 meters as it goes into the equation. We're after the orbital period. We have the mass and orbit radius, so we're going to use Newton's version of Kepler's third law. T squared equals 4 pi squared r cubed divided by g divided by m. We're solving for the period. So you can take the square root of 4 pi squared and do this as t is equal to 2 pi times the square root of r cubed divided by gm. And that will give you the correct answer. So I'm just going to plug everything into the calculator. 2 pi square root of 5,840,000 quantity cubed divided by g divided by 6.39 times 10 to the 23rd power. Enter. And my calculator says the orbital period is 13,600 seconds. It's okay at this point if you round it off. That is equivalent to 226 minutes. It's okay if you express it in units that we can relate to more quickly. We don't know how many tens of thousands of seconds go by during class time, but we do know that it's how many minutes it is. And if it becomes thousands of minutes, we'll turn it into hours. If it's thousands of hours, turn it into days, and so forth. Number 2, a satellite is orbiting planet F at an orbital radius of 11,600 kilometers and a speed of 8.52 kilometers per second. Calculate the mass of planet F. V squared equals gm over r. We're going to rearrange and solve for the mass. The mass is equal to v squared times r divided by g. The speed is in kilometers per second, so we need to turn that into meters per second. So it's going to be 8,520 meters per second, quantity squared. The radius needs to be in meters, so times 11,600,000 meters. Divide that by the universal gravitational constant. 8250 squared times 11,600,000 divided by G, enter. It says 1.26 times 10 to the 25th power. 1.26 times 10 to the 25th power kilograms. Number 3, a satellite orbits planet G with a period of 2.34 days at an altitude of 24,600 kilometers above the surface of the planet. Planet G has a diameter of 12,000 kilometers. Find the mass of planet G. All right. This is really just reinforcement of the same types of problems over and over again. Here's your 3-minute bell. All right, we've had our 3-minute break, so let's get on with solving this problem. Calculate the mass of planet G, knowing the period and the orbit radius means we're going to use Newton's version of Kepler's third law. T squared equals 4 pi squared r cubed divided by G divided by M. And in this case, we're rearranging and solving for the mass. Mass is equal to 4 pi squared r cubed divided by gt squared. The numbers that we put in have to be in the correct units. So let's just do that in real time. 4 pi squared, the radius, so I can do this as open parentheses, 24,600,000 plus 6,000, right? 6 million. That gives me the number of meters, if I put it in correctly. I'm going to cube that, then divide everything by the universal gravitational constant and divide by, open parentheses, 2.34 times 24 times 3,600, close parentheses, quantity squared, enter. So there it is in one shot. I get a mass of 4.15 times 10 to the 23rd power kilograms. So again, a Mars neighborhood planetary mass. Number 4, a satellite orbits Earth. Well, we know the mass of the Earth and the radius of the Earth. With a period of 11 hours, 58 minutes, calculate the altitude of the satellite above the surface of the Earth. Well, once again, we have the radius of the Earth, we have the orbit radius, and to get the altitude, we take the difference between the orbit radius and the planetary surface radius. For the Earth, its radius is 6,378.14 kilometers. Its mass is 5.974 times 10 to the 24th power kilograms. Memorized just because I've worked with it for so many years. And we're solving for r first. We have to use Newton's version of Kepler's third law. T squared equals 4 pi squared r cubed over gm. Rearrange, solve for r. R is going to be the cube root of gmt squared divided by 4 pi squared. So, open parentheses, alpha g times a mass of 5.974 times 10 to the 24th power times, open parentheses, 11 times 3,600 seconds per hour plus 58 times 60 seconds per hour, close parentheses, quantity squared, divide by 4 divide by pi squared, close parentheses, raised to the 3 to the inverse 1 power, enter. All right, so after all that, it says the radius, and this is in meters, so I'm going to divide that by 1,000. The radius is 26,560 kilometers. The altitude is going to be the orbit radius minus the planetary radius. So I'm going to subtract 6378, and I get an altitude of 20,200 kilometers to 3 sig figs. Number 5. A satellite orbits planet D with a speed of 2.34 kilometers per second at orbital radius of 18,000 kilometers. Calculate the mass of planet D. V squared equals gm over r. Rearrange to solve for the mass. Mass is v squared r over g. We're going to plug in 2,340 meters per second squared times 18 million divided by g, enter, and the calculator says the mass of this planet is 1.48 times 10 to the 24th power kilograms.